Hello, so I'm going to give you a different kind of perspective for the software management side. So I'm part of the systems side of things, of keeping the machines running, and some of the problems and maybe some solutions to what we've come into and what we're kind of doing. But it's, I'm going to have a little bit of fundamentals in there, and you may find them humorous, and you may say, oh yeah, is that really correct? But if I can make you think or give you some ideas, then everything was good. So I'm part of HPC Operations. So I report up through Sadaf Alam, and there's three components to this organization. There's the compute services, which is the systems itself. So like Pittsdora, Pittsdynt, and all the other compute systems we provide. Stefano Guarini handles the data-oriented services. That's all the storage. So if you log on to our machines, that's homes, apps, project, even the local scratches on the Cray. And then we have network security and central services, where central services are things like name server, LDAP, things that are essential to the center. The combination of the three of these puts the entire production services in one group. So now we have one integrated group managing all the resources. And for people power, I have 8 people working for me on the system side. Stefano has 6 on the storage, and then there's 3 working on the network security and central services. In this model, we are set up now, in the event we need to grow, we're capable of doing that. We're also capable of moving people around within here in order to meet the demands that come up. So what do? We make the powerful, high-quality computational and storage resources needed to achieve scientific discovery and breakthroughs usable. When a machine comes out, you put it up, you just don't power it on, you just don't log into it and use it. There's a lot of infrastructure work that has to be done on the machine. There's a lot of utilities that get written for managing the system. There's a lot of setup and configuration. So from the system side, that's exactly what we do. And that's where the focus of my talk is going to be now, is what it takes to make it usable. So I've enlisted Einstein. So we have a problem on the machine. So you need a tool. You write it, put it somewhere, call it a day, go home and have a beer. Everything's good, right? No. Well, there's got to be somebody maintaining that. Someone needs to document it. And what happens if the person that wrote it leaves? Where is it? Where's the source for it? So there's a lot of questions and problems. It's not a simple little problem. Bill Gates has a nice quote. Software is a great combination between artistry and engineering. So when you develop these tools and when you provide them to the users for use or to the system managers for managing the system, there's a little engineering that should go into it to make it thorough, make it complete. And the artistry is the style that it presents. It should be very professional. You shouldn't run something and get a weird error message that has no meaning whatsoever. What it produces should be consumable, and the way it runs should be efficient. All right, so let's take a look at the software development lifecycle. I downloaded this image from Google Images. This is a more recent version of this. Over time, it's evolved a little bit. So you start off with gathering the requirements. You have to have a need. We just don't write tools and utilities just for the fun. We have to have a need that we're going to solve. So we gather the requirements, then we analyze that. So if you need to do something, we have to look at it and say, oh, if you're going to need to do that, I have to do this. So a little effort has to go in there. Then the design phase. Now that you know what you're solving and what you need to do, you now need to design the solution. After design is development. These are all pretty straightforward. From development, you go into quality assurance. Quality assurance is also known as testing. And then you go into deployment, which is installing it for general use. And over the years, and through the life of this tool, you'll be maintaining it and enhancing it. And eventually, you'll get some new requirements to enhance it with, and then you'll start the cycle over again. This is a pretty generic, but pretty complete look at what you have to do. So I look back. And I've been doing this quite a while, so I went back to my college, to my undergraduate days, and I pulled out a book from my senior year as an undergraduate. And you can't read it. But what it says, all right. Let's see if I can make it readable. Bear with me. The resolution of the screen isn't very high. So what it was saying is problem recognition for the first one, feasibility study, analysis, implementation, testing, and maintenance.
You don't see it.
Yeah. No, I'm reading it because you can't read it. The screen resolution is too low. Come on. There we go. So if you were able to read this, that's what it would say. So problem recognition, feasibility study, analysis, design, implementation, testing, and maintenance. This was from a class I took years ago. The book was copyrighted 1980. So you have over 30 years now that it's saying exactly the same thing. Yet when you look at the tools that people have provided and the quality that you see, it's lacking this basic fundamental. So people coming into the industry are lacking this knowledge and this ability, taking it forward to present it back out to the users of the systems. So it's a fundamental capability that we seem to have lost, but we need to gain it back.
I don't think we lost it. We never had it.
Okay.
I was software developing in the industry, and it doesn't work like that. Industry doesn't work like that. Nowhere it works like that. What you can do is shorten this cycle into one day, then you have it. This is what happens.
Yeah.
Throw out the quality issue.
I agree. We see too much of this. And I'm going to show in a few slides why I'm pointing this out, because this problem is going to magnify itself very quickly. So Sir Henry Royce has a nice quote. Strive for perfection in everything, take the best that exists and make it better. When it does not exist, design it, accept nothing nearly right or good enough. This is exactly what we do in the systems area, right? We get a system, it's not good enough, but we have to make it better and make it usable for everyone else. And everyone else could be 1,000 other people. So this is defining what we do, but it's also indicating to put that quality, that artistry, that engineering into it to give the best possible solution, which, as you're pointing out, is missing. So here's a magnification of the problem. If you have one computer, that's fantastic. If you have two, that's not too bad. I'm showing a subset of the computers that we run at CSCS for computational work. They're not all the same. We have Crays, we have an IBM Blue Gene, we have different models of Crays, some rack-mounted clusters, different manufacturers. We have a large variety of problems here. If I write a tool for this machine, do I have to rewrite that same tool on another machine? It needs to be engineered to run on multiple machines. I needed to make a change to one tool, and I asked one question. Where's the source code? 2 days later, they found it. Now, if you have to ask that question and someone can't say, it's in this directory, then there's a problem. And I have a few other of these questions at the end that I'll run through. So, how are we going to solve this? First is to develop a plan. So, I have a very large system programming background, and I'm able to bring that forward into my team and guide them through the process to elevate the standards, to actually do some of this in their day-to-day work and show them how if we do this, it will be better going forward. When we bring in a new machine, it shouldn't take us 3 weeks just to put the tools we need on it. We should be able to do that in a day or two. In most cases, you should just be able to load it, compile it, you're done. And that's where we need to get to. And that's where defining the process is. So once we gather all the tools, once we package all the tools, we can then define a process for installing them. Whether it's through an automated tool or manually, we can still define that process, and it will be the same for every machine. And that will save time going forward. Standards is a often overused word. When somebody says use a standard or a standardized process, you typically go out and look for a book with something that says, oh, that's this number that represents this. But in this context, think of it as a consistent way of doing things every time. So if you have a consistent way, you're going to do the same thing on machine A, whether it's a Cray or a Blue Gene or a generic cluster, and they're all the same. So the same person doesn't have to know the intricate details about every machine. They just need to know how to do it. And that's where training the staff comes in. Having this wonderful process is great. Telling everyone you need to do this is great. But if you don't explain to them and work with them on how to do it, then you're not solving the problem. You're not giving them the knowledge they need to do that. So you have to build that level in the staff itself. And then talk is easy. Put it into service. You have to implement what you decide. And that's the next one. And the last one is enforce it. It's great to say, we're going to do all this. Everybody's gung-ho. We go out and we do it all, put it all in play. A year from now, everybody forgot all about it. No, once you start it, you have to stay with it. Otherwise, you're back to where you are now. So, how can we reintroduce design, artistry, and engineering into system tools? It's an interesting question. A lot of system admins don't think there's engineering behind what they do. They don't think there's any artistry in what they do, but there truly is. They have a knowledge level that they're imparting into whatever it is they're developing. Albert Einstein had some wonderful advice. Make it as simple as possible, but not any simpler. I've seen some code in my time that was so complex that it took days just to understand what a little piece of code was doing, only to spend 5 minutes to fix it. So you have to weigh this. Complexity is not necessarily a solution. You want to solve the problem, but you want to solve it so that it can be maintained going forward. Which brings up the last question, what are we going to do? So I've laid out the fundamentals of the problem, and now what are we taking steps to do to improve this so that we're positioning ourselves for when we bring in a new machine, when we retire a system, how can we keep moving forward without having to re-implement or reinvest time in developing a whole new solution every time? So structured components. I've made it a point that everything we develop now will have a makefile. Do you think, oh, what's the big deal about that? Yeah, there's a little script. Who needs a makefile? Well, what does a makefile do for you? It eliminates any questions about what it takes to build it, what it takes to install it. And it does the same thing every time. So if we have this bundled up with a makefile, I can say, you just need to go in there and type make clean, make, and make install, and you're done. So it's a very simple little thing, even for the simplest of script. Now you look at it from one script, you say, that's not a big deal. What happens if you have 100 utilities you're maintaining? So the problem just gets bigger and bigger. Man pages. Now everyone in this room has probably written a utility or two over the course of your careers. How many have actually written man pages for those utilities? And then how many times have people come up to you and said, how does that work? What are the options for that? It's a simple thing to do. Write a man page, write documentation. It'll also give you a professional quality look and feel. It'll look just like it came with the system itself, which gives a level of confidence to people. It gives them a comfort area. Maybe they'll use it more. But it's a single point to go for documentation. And it's integrated into Linux. Command line help. So I once used a utility written by someone that took 24 different options. No man page, no command line help. The only way to figure it out, and this was an executable and we could not find the source code. Yes, because that person left. So how did I figure out how to use it? I had to dump the executable and actually pick out all the options and figure out what it did. There's no need for that, right? Why not just put a -h inside there and say, here's all the options you need to use. Very simple thing to do. Take you 15, 20 minutes to complete, and now you have some inline documentation. Revision control, whichever system you choose. You'll have a repository now that you can always go to for your source code. Most scientists are currently using that, but I do know some that aren't. And I've actually seen some have catastrophes when they overwrote their files and they couldn't get back to them. And it's like, well, you have the tools. You have to use them. And consistent installations. I just showed you a slide with about 8 machines on it, and we really have more than that we're running. If I install some command in one directory on one machine and a whole nother directory on another and a whole nother directory on another, how do you know where to find it? Why can't it be installed the same place, the same way on every machine? Now you have a nice consistent location to find everything. And naming conventions. I'm going to show you an example of this, but how many people have ever named something, name word underscore word underscore word underscore word underscore word dot some number dot sh? Why, right? And you see this everywhere you go. Let's dig a little deeper into this. So just look at a Makefile. What can it do for you? And if you go out and look at places like Wikipedia and other sources online, they'll quote Make as a utility for maintaining consistency because it does the same thing every time. There should be 4 targets inside your Makefile, not just the normal 3. Everyone usually does a make, right? So they put the build in there. If they're lucky, they'll do an install. If somebody's been bitten by it, they added a clean. Well, 4 years down the road, you decide you no longer need this utility. How do you remove it from your machine? You have to look at the Makefile, you have to figure out where it installed it all, and then you have to remove the files manually. That's okay for 1 or 2 files, but what if you're removing 100 files? That's very tedious. Very easy, add an uninstall. So 4 basic targets inside a Makefile makes things real easy. You get the same permissions on every machine you run it on, every time. You get the same ownership every time, and it goes in the same location. And I'm pointing out here, regardless of how the tool is developed. It could be a Perl script, it could be a shell script, it could be a compiled program. Everything should use it and be organized that way. I'm a strong proponent of man pages. It's an easy way to do documentation. In my career, too many times I've had to go and knock on a door and say, what did you do here? How does that work? What's the options? I want to just say man, the command, and I'm done. The only requirement, it needs to be in your man path. Very simple thing to do. You can do it through modules. You can put it in your profiles, anywhere you want. But it's a very simple little thing. It's also a standardized format within Linux. So under every Unix machine out there, you can write a man page and boom, you're done. It also has a well-defined structure, right? You have some prefixed path to a man directory, which in it has man and numbers and cat and numbers. So all your manual and catalog pages are all in a predefined location. You know where to find them on your machine. And it's a very easy way to find usage. Not only is it easy, it's consistent with the rest of the machine. Revision control, well, here's where there's a lot of, I'm going to say, religious debate over which way you do this. People have preferences, fine. In my opinion, they all serve a valid purpose. They all can do a job. You have to choose the one that you need that works the best for you. Git and Subversion are two very popular ones, and they work in a sort of distributed fashion. Git is nice. You can actually download the repository, and you can do comparisons back to a master repository very easily, so you can know if there's somebody's checking in changes and you're not being told. There's also the long history of CVS, which is the evolution of RCS, and some newer ones like Vesta and Mercurial. These are all options, but there's a lot more out there. You can go out to Wikipedia and type list of revision control software, and it'll give you a whole long list of open source as well as commercial products. Configuration management is also key. Now, having a consistent build and install mechanism is fine, but you also need to maintain the structures to support that. For example, you're going to be installing your software somewhere. Where's that directory tree maintained that you're installing it into? Or are you expected to go out to the machine every time you bring in a new node or a new system and type make dir, change own? No, use your revision control system to do it. So at CSCS, we're using Git, and we're integrating it with Puppet. So the combination of the two will give us our revision control as well as our configuration management. And I list out a whole bunch here. You've heard a little bit about Ansible earlier. The other two, another popular one is CF Engine, but Chef, Salt, Rex, there's dozens of them out there. Again, you need to choose the one that works the best for you. You could also go out to Wikipedia and get a whole list of them, and it's a pretty long list. So I talked a little bit about file systems and the structures that you install into. There's actually a specification called the Filesystem Hierarchy standard, which defines the purpose of each directory in Linux. So you can go there and you can see what it is you're supposed to put in there. I've seen in my time people installing commands in the etc directory. Why? They say, oh, well, it's a script. No, it has a defined purpose, it has a defined location. So you can go out and look at it. Now, when you look at a standard like this, it's written very specifically towards the operating system to present the operating system's view. But it's very easy to adapt it out to system tools and packages you provide. Bin, you know, we're all familiar with user bin and bin itself. Those are user level commands. Very simple. sbin, system level commands. So if you're intending for your users to use it, then you just put it in bin. If you're intending it to be run in support of the users, either to administer the system, or maybe your user support organization, you've provided them a tool to work on behalf of the users, you put that in sbin. Your manual and catalog pages, nice location for it. You just design the structure below it, and everything is good. Just add it to your man path, and you're all set. Include in lib, maybe you're providing an API. I don't know, but it's there to allow that. And perhaps you're installing other packages. Maybe you've downloaded some open source software, which comes with a nice package. You should format it up into a nice structure. Put it in opt. Now you have a nice location. And it all follows along with the guidelines of actually Linux. The only thing left, you define the prefix to get to this. And you could have more than one location. For example, we use globally mounted file systems. So one file system mounted across all our production systems. What happens if I have to compile something for a specific machine? And maybe I have to compile it for all of them. And the executable is not compatible on all the machines. So you really need two locations, a common one, so now you have one location for it, and one specific to the machine, but the structure should be the same. And to create and maintain this directory should be through a configuration management tool, whichever one you choose. Now when you bring in a new machine, you run your configuration management, it creates the structure, you now download the software, you build, install, you're done. Naming conventions. So I mentioned this. Remove name from list.sh. That was a real name. So the first question is, why do you need the .sh? If you want to know what an executable is or what a command is, you type what in the command and it tells you. Or file and it tells you it's a script and you can look at it. So you really don't need to put that suffix on there. But I have a few suggestions for prefixes. Now, a lot of people will say, I need to do remove. Well, I need to type the word remove. No, rm. So if you want to change something, ch, create something, cr, list, ls, make, mk, rm for remove. So now you have a set of prefixes for any command you develop that could be consistent and provide a nice, easy interface to the users or to your staff. Oh, I'm hoping this shows up. I don't know if anyone's played with source code documentation. There's several systems. This one is Doxygen. So you instrument your code with directives all the way through it, and then you ingest that into the Doxygen engine, and it produces an RTF file that you can feed into Word and produce a nice document out of it, HTML version, or it even produces man pages for the various components. This one is for a utility I wrote, and I want to show the value of using tools like this. So I did this not expecting to find anything when I first documented it and was preparing to make it available. And then I realized, all right, this has a laser pointer on it? In the middle. No. We have to turn it on. There it is. So here's the main of the program. This is a function for producing command line help called usage. And this is another function for version. How do you end up in your help text? Somebody types -h, or you type a bad command line option, and it usually gives you command line help, right? But notice this other line coming from this other function. So I looked at this when I generated it, and I said, oh, that can't be right, because I know the only place you call for help is from main. So with this tool, and I actually have it running. Let's see. So this is the interface to it. File list. And I'll bring it up. I'm hoping it shows up there. And here you can see that line I was talking about. This is just a simple source code documentation tool, and now I'm seeing a dependency that I don't understand. So with the tool, you just click your way through it, right into this. You can see the function itself, but I'm going to go right into the source code. So it was called usage. So I can hover over it, and now I can see what it thinks usage is. It thinks usage is the function usage for displaying help. Now in C, this is still valid because of the context of the variable. But in programming, it just created a huge amount of confusion because of a variable overload of the word usage. So here, you can see the value of looking at the output of a tool. So not only do you need to use it, but you need to look at it and understand what it is you're looking at. Okay, so now you're organized. Let's assume you've collected everything together, you've repackaged everything, everything is nice and clean, it's very consistent, you have a good location to install it, everything is well defined, you're well organized. Well, you bring in a new machine, do you really want to go one command at a time saying make, install, make, install? No. You want to automate things through whichever tool you choose, and later on you're going to hear about Easy Build again, and we heard a little bit about it earlier. But you should set defined objectives as to what you want to accomplish by automation. In my mind, we want to be able to rebuild all tools and packages. I want to be able to say, do it, and not have to worry. And it will go off, do everything it needs to do in the right order, and finish up, and I'm done. It needs to be able to install all tools and packages. Again, I don't want to have to go through it one at a time. When a new system comes in, or a new node, and you want to install into it, it should be able to do everything for you. One command, do it all, you're done. Now, take this, combine it with configuration management. So you have your build automation, which handles that portion of it, and then you have the configuration management, which handles the system side of it, where you're installing into. So the combination of the two is very important. You can go on to Wikipedia and you can type list of build automation software, and it'll give you a whole big list. Commercial, open source, a whole variety of them. But I want to caution you about some wording. There is a difference between continuous integration and build automation. One of them provides you the ability to rebuild your software and install it. Continuous integration adds in the testing functionality so that it continuously builds and runs regression against it. Continuously builds, runs regression. So you need to choose what it is you really want. For system tools, we don't need continuous integration. Typically, we build it, install it, test it, we're done. And it sits there until we have to modify it or rebuild it. We don't need to test it every night or recompile it every night. So be careful about what you choose. Some tools will do both in one tool. Ask yourself if you need the complexity of that tool. Right? Some of these are very easy to use, some are more complex. Again, there's open source as well as commercially available products. So I thought I'd ask a few questions. Have you ever had to ask where the source code for anything is? And of course, we all know where all the source code for everything we ever write is, right? So this is fine if you're the only one doing it. Of course you know where your source code is. What happens if you win the lottery and you move to some nice, beautiful island in the South Pacific? What's the next person going to do? They're going to go, oh my God, I don't know where the software is. So that's a really good question. Have you ever asked how to rebuild something? Now, most packages, you type configure with a whole long list of options. And it usually generates a config.log that you can actually go in and look at. But I know a lot of people that remove that log file because sometimes it's too big or it's just too noisy to keep there. So what were the configure options that you used to build that version of the software? Right? And the last one, have you ever said that you wished there was a man page or command line help? Right? Ask yourself, did you ever run something and go, what were those options again? Or you have to go through a notebook and find out your notes for it because it's not documented anywhere. When 20 minutes you can have a man page and command line help. It's very simple. So these are some key questions that guide from the system side the need for this. And when you combine it with the multiple systems, multiple architectures, and the evolving systems, right? We're moving forward, bringing in new machines all the time. This is very key. And with that, I thank you for your time. And when all else fails, just a clear plug, call your sysadmin. They can fix anything.